Okay, this is the case of low correlation. We have to take a look at that. Once you plot the scatter plot, you see the trends, right? There are certain trends. You can probably want to ask what types of lines that you can fit into the data. Because the data kind of scatter, right, in the scatter plot, if it shows patterns that you can probably draw a line to that. What types of line would you draw? Should best summarize the relationship between them. So we have to take a look at what type of line means what parameters that the line should contain. For the lines, we can explain the line using the line equation. In the line equation, we have like yi to denote the actual response of the experiment of unit I, or the observation at unit I, and xi would denote the predictor or the input of unit I as well, and the y hat here would be the predicted response. And then we can write the line equation as the y hat I would equal b0 plus b1 xi. That means instead of yi and xi, right, initially we would have that and plot it as scatter plot, we derive the new values of y, right, using linear equation b0 plus b1 xi. Okay, so this would be the line. That means our jobs now would be finding b0 and b1 to explain, to draw a line basically. Okay. So let's first understand what effects that b0 and b1 would be in terms of the data. Okay, b1, right? b1 in this equation indicate the slope. There might be different notations when you read different books, when you watch different lectures, but just denote whether they are the coefficients of the variables or whether they are just the offset or intercepts here. You find it everywhere, starting from like linear regression here, the basic linear regression, up to studying about deep learning. There will also still be this type of offset. Okay, so like I said, just take a look at the notation, and the nature would be similar. B1, right? B1 indicate the slope, will indicate the size of one unit change. If x change 1 unit, what size of change would y contribute? Okay, and b0 will indicate the intersect of y at x equals 0. Or in other words, if there is no x, what should be the value of y? That would sometimes refer to as backgrounds or offset, right? It refers to something like the, or if we talk about, for example, when you look at the Rotten Tomato rating, I suppose you should know, right? Or IMDb rating, movie ratings, there will be some types of background or the average value, and that's b0. But maybe rating will change depending on the types of movie, that's x, and you kind of explain x change. When x change, what rating will change, that will be b1. So that's the analogy there. Okay, in our sense, we have, like, if we have this, like I said, the notation, just because I create multiple version of lectures and sometimes got reference from elsewhere, and this is b0, this is b, and this is b0, b1, but alpha and beta is the same things. So you have the dot here as data points. The red dot here are the data point, and the dashed line here indicate the model. The model is explained by alpha plus beta xi, but you can see that the dot itself is not on the line. That means if you want to explain the value of the dot, the yi would be alpha plus beta xi, or this one, plus epsilon. Right? Epsilon is the green line here. It indicates the errors or the variations of that occur from when you explain data using lines. Okay, in linear regression, there is a basic assumptions that the error should be normal distribution with mean 0 and variance sigma square. Right? Anyone, can anyone tells me why is that the case, that it has to be 0 and sigma square? Why is that the case in terms of the epsilon, the error? Okay, you can either talk or you can type. I'm fine with the streamer ways. Type and read that, right? So why is that? Why error has to be normal distribution with mean equals 0 and variance with constant value? Any answer? Why n0 and sigma square, right? This is n0 and sigma square. Should be normal distribution. This assumption actually, yeah, we got some answer here. Because if it's far from the line, it would be effect data. Almost there, but not right. Any more answer? That's actually a good explanation here of normal distribution. Any answer? No? Okay. Normal distribution means that most of the value would cluster in the middle, right? Reverse bell shape. Mean equals 0 means that on average, the value cluster at zero location, at here. That means most of the dot would be around the line. Right? It would be around the line. If mean is not 0, it would mean that the error itself has more positive value than negative value, right? If the error, if this is positive, it would be that the error has more positive than negative, and that would indicate that the line might look not like this, but oops, let me find this. How come I can? Okay, but the line might look like this, and this would create n and then something positive and then sigma square. Because if you compare this to the line, then most of the error would be more than 0, more than 0, right? And only few of them would be less than 0. And you can see that it doesn't look good in terms of the fitness of the model and the data, right? So if you have like positive here, it would be it would look like it, and this can happen. Right? How come it can happen? Suppose that you have outlier here, and then you fit the line. Then the line may be pulled down because it's nevertheless linear regression based on the model of normal distribution like this. It is affected by outlier, and it will pull the line down. Okay, so if you have positive positive means in the error distribution, then that means the bad. That means bad, right? That means it's not a good case there, not a good fit. Same go for negative value. If you have negative value, it means that the lines kind of go above the points. Right? Line go above the point, you would have negative mean. Okay. So all in all, this is why you need to have like n0 sigma square, right? Sigma square here to indicate that when you have when you look at the variation around the line, it vary equally throughout the line. So it means that the dot should be above the lines, not far apart on some part. Okay, so this is the reason that the error should distribute in normal distribution with a mean 0 and variance sigma square. Okay. Now, which line is the better one? This one or this one, right? There can be multiple lines if you draw between the data, right? But which line is the best? Which line is the best? We want to find the best line to get the best parameters. Should it be this? This is the line that passed through as many points as possible. Or should it be this line? The line that minimize the maximum error, right? Minimize the maximum residual of each point. What does that mean? It means that this line would be in the middle. Or should it be this one? This is the line that say divide the data into two parts. Each point carry the same weight. Which should be the case? 1, 2, or 3? Right? 1, 2, or 3? One, 2, 3, 3, 2, 1. 2, 2. Okay. Good. Right. Number 2. Right. Actually, it's number 2, and it's the basis of the method called the least square. A method that we will take a look at how to optimize it. Why is that the case? Because as in the earlier assumption, you want a line to draw in the middle of the cloud point, and that line would have mean 0. The errors that occur from drawing that line would be 0 mean and variance, constant variance. To do so can be done by minimize the maximum residual, right? So what is residual? Let's take a look at each bit first. What is residual? Residual that's spelled like this. Residual is an error of each point. So if we predict the value using this b, let me change it to this one. Using this equation like b0 plus b1x. b0 plus b1x, you get the predicted response yi hat. This is the predicted response. Subtract it out of the actual y. This is error, right? This error is referred to as the prediction error or the residual errors, or the remaining. Residual means remaining. Okay. We want a line that would minimize this error. So this error would be the smallest, but not just 1 point, not just 4 points, but for all of the points that you have, for all of the data that you have. So it means that we have to calculate the sum of this error through for the whole data set and form the error function. Okay, this is the error function which comes from the sum of the error, right? Sum of the epsilon here, and it comes from the summation of the actual value minus the line, right? This is the errors, and square, sum together. We want to minimize this function. Okay, we have a question here. No, not questions. Never mind. All right. Okay, so if we take a look at the error first, and then we will, no, never mind, don't worry. Okay, take a look at the error first, and we will take a look, once we see which one is better between the two lines, then we will try to find a way that we will get the best B0 and B1 out of these equations. It's actually the basic technique that you learn in your calculus, that you have been wondering, why do you need to learn calculus? Now here, to study data, you need calculus. But well, we will take a look at that later on. Okay, so summing the error get you which line give you the best one. So comparing between these two, right, the 300 and the minus 300 and the minus 200. Okay, if we calculate between them, the first one will give you the residual here, like this column, and calculate the square, and sum them, the dash line, the minus 300, you get 766.5 values, error here, and for this minus 266, you get 597. So now which line is the better one, the dashed line or the solid line? It should be the solid line, right? The minus 200 one, because you can see that it has lower errors, right? This one has lower errors comparing to the first one. Potentially, probably because these 2 points kind of far off from this one, the line shouldn't exist there, right? All right, so now we'll take now we see that the lower error indicate better fit.